or sequences, if you want to call it. And we looked at traditional way of analyzing or forecasting a time series, which is using ARIMA. And then in the last tutorial, we looked at neural networks, how we can use those for time series prediction. Now, the latest happening thing in sequences or analyzing sequences and forecasting is recurrent neural networks, specifically LSTM, which I think is probably the most famous form of recurrent neural network. So let's spend a few minutes, hopefully not too long, understanding LSTM, and then continue this time series forecasting in the next tutorial. And then in the one after that, let's see if we can actually apply LSTM to some sort of natural language processing. I know these are all supposed to be like for researchers and image processing, but if you think about it, time series forecasting is part of any scientific research, and natural language processing may not be, but if you really want to automate a system to read a whole bunch of papers for you and then prioritize the papers based on the content, then just think of writing some code for a natural language processor, to actually understand what's going on in the paper and then kind of summarizing it for you, okay? But anyway, before we jump ahead to all of that, let's understand what LSTMs are. So first of all, let's have a quick look at what our traditional deep learning is. Again, if you have watched my previous videos, or if you come with this background, you know what we are talking about, which is a traditional deep learning is, okay, a specific example in this case, I have an image, what is it? Is it a cat or a dog? Classify it. So the way we deal with this when it comes to image analysis especially is use convolutional filters. Why do we use convolutional filters? Because these are two-dimensional filters that are convolutional filters, as the name suggests, and it extracts various features from the input image in a very cascaded way, in a step-by-step way, I should say here, and a patch is applied, features are extracted, and then we do some operations like max pools and others. Eventually, before it goes into this fully connected layer, we generate a whole bunch of features as inputs to this dense layer or fully connected layer or feed-forward layer, and then the information goes through in this direction, and eventually what comes out is a probability. Again, it depends upon what types of activation functions you're using, but typically a probability saying, okay, your cat, it's a cat with 80% and it's a dog 20%, so we finally say, okay, that's a cat. This is our traditional deep learning, okay? So all the information it needs is in this image, and all the information is transferred, one after this other. I mean, in all these images, one after the other, and then they go in. So at no point, you can see the direction here of information travel from left all the way to the right, okay? But in a time series, just the feed forward doesn't work. We also need to send some information back, so this neuron actually has an idea of what happened in the past, in the history, when information went from here to there. It may be confusing, but we'll get there, believe me. So the summary of this slide is recurrent neural networks are different from regular neural networks in the fact that they remember the past, okay? RNNs remember the past. That's the summary. Now, how do they do that, or what do I mean by that? Like, why do we even need RNNs if we actually have, traditional neural networks? Well, think of this scenario. If I'm thinking about what's for dinner, and if I have a pattern, I start a pattern on a Sunday. I say, okay, from now on, I'm going all Asian diet for the next couple of months. Today, I'm going to have, or on Sunday, I'm going to have Japanese, and then Chinese, and then Thai, and then Indian. And then I'll go back to Japanese, Chinese, Thai, Indian. Obviously, I'm traveling west. Okay? And so on. Okay? So I go through these. There is no pattern here with respect to the date. It's not like on Sundays I'm eating Japanese, because if you look at Thai, I eat Thai on Tuesdays, on Saturdays, on Wednesdays, on Sundays, Thursday, Monday. So there is no correlation between these two columns. There is correlation between this column itself, between different data points. This is what we call autocorrelation. I talked about this in the first video of this time series tutorial. This is why we need RNNs, because regular neural networks, the typically we have X, we have Y, X and Y, right? And we are modeling this X to predict Y. But here we have to model Y to predict Y. Okay, because what I'm going to eat tonight depends on what I ate yesterday and the day before, not on what day it is. I hope that point is clear here. Okay, so that's RNNs are designed to make use of this type of sequential information, and let's see why. Okay, let's go through this step by step. Now, first of all, an RNN is, if you see a diagram, a picture like this, by the way, I should credit numerous sources. I should have taken better notes to give proper credits here, but most of these images I completely took from my Google image search. And go ahead and do Google image search for RNN, you'll find these pictures. Okay. Now, if you unroll an RNN, okay, which is what happens during the execution, okay, during the training and prediction part, this is an RNN. As you can see, the input is coming from here and there is an output there, but then the information is traveling back within this cell. So this is a RNN cell. What happens? So that if you unroll this, it's like the same network. There are multiple copies of the same network, and each of this is passing on information to the next. Okay, and you see how this is like a nice list-like structure or a sequence-like structure. That's why these are very good for sequences. Okay, let's dig a bit deeper now. Okay, so there are many types of RNNs, although LSTM is the most famous one. But let's understand, one-to-one is just like a regular neural network. Okay, you have one input, one output, so it's like image classification. Okay, cat, dog. So that's a typical one-to-one. One-to-many is like image captioning. You supply an image, okay, a cat in front of a car. Okay, so it's outputting a sentence. A cat in front of a car. Okay, it's explaining a scene. So this is one-to-many. Many-to-one is exactly opposite, which means there are multiple inputs and only one output. So typically sentiment analysis. A bunch of tweets, for example, you supply a whole bunch of tweets on a specific hashtag. It says, well, it's not good, or wow, excellent. Okay, something good happened. So it's for sentiment analysis. You can use those type of RNNs. There is something called many-to-many, and there are many variations of many-to-many. Okay, and this is for language translation. So if you supply like a sentence in English, it's giving an output in German, for example. Okay, so that's many-to-many. So there are many variations like this. Now, I'm explaining the problem with RNN. Life is great, then why do we need LSTMs? Well, if you look at this sentence, the sky is. I'm pretty sure most of you will answer by saying blue, unless you are in the San Francisco Bay Area. I cannot turn my camera, but the sky outside is red because of forest fires and everything. Anyway, if I give this sentence, the common answer is blue. So RNNs are excellent at doing this because very short sentence. If you have a long context, I think I did put this wildfires, yeah. So this is the 10th day of wildfires in the San Francisco Bay Area. There is smoke everywhere. It's snowing ash, and the sky is. Now the answer is red because there is some context here. So the sky is blue is probably not the answer, right answer here. How does an LSTM know this? It doesn't remember. I mean, how does a RNN know this? It doesn't remember this much of this. Okay, it looks at and the sky is, and then it's trying to fill this with blue. Okay, this is a limitation. I'm not sure if that explanation is clear enough. But the quick answer is a lot of previous information is necessary to get the answer right. Okay, and RNNs, they fail. Theoretically, they should be able to do it, but apparently they fail. Okay, this information is here about wildfires, and the sky is information prediction is right here, and it's getting it wrong. This is why LSTMs, in fact, the LSTMs, I think I should have included historical information. The concept of LSTM was from 1990s. So it stands for long short-term memory. And of course, it's designed to overcome the limitations of RNN, which is gradient vanishing and exploding, meaning the gradients in the gradient descent, they go to either 0 or they explode all the way to infinity, or if you want to say 1 is maximum. So why? Again, that's a different discussion. So that's a problem. And LSTMs are designed to overcome this. Also, RNNs can be very complex to train, and more importantly, difficulty to process very long sequences, which I just talked about here, okay? And remembering this type of long information is intrinsic to LSTM, okay? Again, please read papers on LSTM if you're curious about it, but I'm going to explain it a little bit more in the next few minutes. This is a traditional RNN, where information before is taken in and passed on to the information to the next cell with some operations happening in this cell, okay? What's happening in this cell? It's taking an information from here and also from the previous cell. And it's applying a tan h. Tan h is basically -1 to 1, okay? And then sending the output, which means it is taking information from before, okay? So this is what RNNs are for.
I serve for the place I call home.
I serve to protect those around me.
How does LSTM differ? Excuse me. LSTM looks, again, in an image, it looks somewhat like this. So it's not just a straight tan h. Of course, you have that component here, but in addition, you have a sigmoid, and a sigmoid right here, and a tan h over there. So let's deconstruct this and then look at this one at a time, okay? So a closer look. So first of all, if you look at this first part, in the top part, for example, you see the information is going in a straight line right there, and let's call that the cell state, the state of the cell, okay? So it's in a certain state, and to that we are supplying, here we are multiplying whatever this value with the state value there. So the cell state is modified. If that value is 1, then we are not modifying the state value. Here we are doing an addition right there, okay? So this is the state. Now what is this first part? This is what we call a forget gate. As the name suggests, gate means it either lets something in or doesn't let it in, which means it helps us, the forget gate, okay? It helps us in defining what information to forget, what information to remember. Next gate, input gate. We'll look at this in a minute. And this also obviously controls the amount of information that goes through. And finally, the output gate. Also, we are doing some math before we send it to the output. So now let's actually look at this. The top part we already mentioned. The information flows through this path, let's say. Okay, so you have some information flowing through, and the gates are letting the information through the cell state. Okay, so the forget gate can be 1, and then it multiplies this information with 1, so nothing gets forgotten and everything goes through. Okay, so, and this is the next gate and the next gate and so on. And you see these sigmoids and the tan h, and if you ask why sigmoid and why tan h, then the answer is the sigmoid is outputting a value between 0 to 1, right? Sigmoid is like this S curve, and the output is 0 to 1, and it can be used to forget, remember information. 0, okay, completely forget. 1, okay, just let everything through, right? So that's why sigmoid is great. And tan h goes from -1 to 1, and it's a great function to actually add weight to individual values, but it's there to overcome the vanishing gradient problem. Okay, again, if you look at sigmoid, for example, the second derivative, they do not sustain, the first derivative is fine, but the second derivative goes to 0. So, but if you look at the tan h, the second derivative still sustains for a long range, even before going to 0, even for second derivative. That doesn't make sense, fine. Let's move on and understand the forget gate, okay? The math is right here, because you have a sigmoid function, you have some input coming in, you have some historical information coming in from the previous step, which is time t minus 1, and then there is some sort of an output that you're multiplying to the main information over there. So like I mentioned earlier, the outputs, sigmoid outputs a number between 0 and 1 after this operation, and this is for each number, it's how much information to keep. And the next is the input gate down here. Of course, what new information will be stored in the cell state, because there is information coming in. What new information will be stored in that cell state? Here we have a sigmoid and we have a tan H. Okay, and don't worry if you don't understand any of this. Wait a couple more slides, you'll see how easy the implementation is in keras, but please try to understand what's going on inside LSTM. So the sigmoid layer decides which values are updated, and the tan H layers are deciding the weight of each of these values. Okay, so the importance of each of this value. And moving on to the output gate, which is the last one down here, again it has a sigmoid right there, and the sigmoid decides which part is again selected for the output. That's what sigmoid is. And the tan H gives, as usual, the weights. Yeah, the tan H right there gives the weights to this incoming values right there, and then a multiplication operation right there, and that's what's outputted, that you get as an output right there. So hopefully things make sense. If you actually look at each of these, it's basically a bunch of math going on. Information coming from here on, when I say information, a vector, a bunch of numbers are coming from here, a bunch of numbers are coming from here. There is some math going on, which is a sigmoid, which goes from 0 to 1, and then there's a multiplication there, information coming here, and then a tan H type of activation applied to that information, and then this value is multiplied with this, so you get an output right here. So it's like looking at an engineering diagram, right? I mean, you just follow through and hopefully things make sense. Okay, how does it look in keras or in programmatically? If you look at this, very simple. We use sequential method just like we do for any other neural network using keras, and then instead of 2D convolutional or dense layers, we are going to use LSTM. Someone else already did the hard job of designing or defining this LSTM, so we just call that method. Okay, so LSTM, how many units of LSTMs? How many units, right? I mean, I just showed you 1 unit of LSTM. How many units do you want in that layer? So 50 in this example. And when you say return sequences equals to true, that means yes, return that, so I can stack another LSTM, okay? So that's what you do over there, and because this is also the input, taking in input, we are defining the input shape, okay? So you have your input layer and LSTM. To this, dropout is regular dropout like regular neural networks, meaning from this LSTM to the next one, I'm dropping 20% of the data and keeping only the remaining 80%. This is optional depending on how your data looks. Next comes next LSTM, same thing, units equal to 50, return equals to true, which means I'm providing another LSTM down here with a 50. So here, this is a stack of 3 LSTMs, and the output is a dense layer with unit equals to 1, which means my output is only 1 value after this. Okay, so that's what this, and then the optimizer is Adam and loss is mean squared error, which is very similar to what we have done in the previous tutorials. As you can see, if you have done your regular neural network, this is very similar, except you're just using LSTM here. That's it. Okay, so now there are a few more variations of this LSTM. Go ahead and learn about bidirectional LSTM, because LSTM we just talked about one unidirectional. But if your series has meaning in both directions, like in the forward and back direction, then bidirectional LSTM can be a useful one. Now convolutional LSTM is also something that's available as a single line, that you can apply. So go ahead and read about it in next video. I'm going to demonstrate all of this on a time series data. Okay, I'll probably include bidirectional and conv LSTM. Whether I demonstrate or not, I'll share the code so you can test it yourself. Okay, so I really hope you found this tutorial to be educational. And in the next tutorial, let's apply this knowledge onto an actual time series so we can do some forecasting. Thank you very much, and please subscribe to this channel.
So, did you all enjoy the video? Okay. So do you guys have any questions, or should we move on to coding portion, or? If no one has a question, I guess I'll move on to coding portion. So let's see. What we'll do is we'll go to a collaboratory. So collab. Can everyone see my screen? Is everyone seeing my Google Colab or no?
Yeah.
Yeah, I think you're seeing my Google Colab. So, yeah, you guys are all seeing my Google Colab screen, right?
Yes.
Alright, thanks. So, okay, so now we're gonna import some libraries first. Import NumPy as NP. And what NumPy is, it's a very useful library for matrix. And all the data is all about matrix, and that is why we need NumPy. It's a very useful tool. TensorFlow, keras datasets import. So IMDB is a dataset name, so we're gonna download the dataset. Okay. And then now we're gonna split into training dataset and testing dataset. Test all. Y train all. Test. Y test. IMDB.load. Data. Skip out. Number of words. So what this means, we're gonna skip the top 20 words that are frequently used, like or the or a preposition or top words that are frequently used that are not very important. Then we're only gonna retrieve 100 words. So we're gonna split into training and testing sets. Okay, so downloading is complete. Now we're gonna see what the training set looks like. Oh boy. So this is the sentence. For example, like I did enjoy the movie. Like this could be the sentence. It's only words that are matched with the numbers. Now we have to convert into words. This is one sentence that we have retrieved. So now we're going to do for I in range, train all. Train all. I is equal to W for W and X train all I W to train all 0. So what we're gonna do is we're gonna skip the first two words are not actually a words. That's why we have to skip. So this is a for loop in order to skip the two unused words. Train it. Now you can see how the twos are deleted because it's less than two. It's not greater than 2. This is deleted, so 22, 43, 65, 66. And now we're gonna download a dictionary so that we can convert the numbers into actual words. Word to index, IMDB.get, word index, word to index, movie. So we have downloaded a dictionary that will allow us to match word for a number. Okay, now we're gonna convert, so right now we're gonna convert the number into words. Index to word, word to index, okay, okay, word to index, boolean. For W in X tree all 0 X to word W minus 3 and yeah, so what we have in here, we have just converted it. It is saying film the story really. They you just there on from. So it's all like a little bit ununderstandable because we have taken out the most frequently used words. And we have only downloaded 100 words. That is what's not understandable. But this is the main words. Anyway, we only need main words in order to use it. So this is sufficient. So these are the data sets that we're gonna feed into a model. And then let's see. So now we're gonna what should I say? Split into training set, validation set, and testing set. So np.random.seed. Seed is just like the seed in Java, where this allows be randomly distributed. Train all random index 20,000. So we're first getting the first 20,000 for the X train. Y train all random index 2. Yeah, same thing here. We're setting the first 20,000. X val validation set. We're splitting the training set into training set and validation set. Random index 20,000. Whatever is left is going to validation set, which means 5,000. Train all random index 2. So we have a training validation and testing data set. Okay. Please feel free to stop me if you guys have any questions or want me to slow down. Okay. Now we're going to use a library function. From the Tensorflow is a primary library for machine learning. There's the pre-processing report sequence. Max length is 100. Train sequence. Add sequence. X train. X train. X train. XL sequence. So we're padding more numbers in order to provide the same shape. Sequence add sequences XL X length X length. Yeah, so what we have just did was putting some padding, and padding is arbitrary numbers such as 0. We're just putting it in. So if you want to see, it'll be like this: print X train sequence 0. You can see how you put more zeros padding in order to provide the proper shape. And then now we're gonna do one hot categorical function. It's hard to explain. One hot categorical. Okay. So I think. Yeah, I think this is good. Is everyone seeing my Google screen? I assume everyone is. So what one hot categorical is so we originally have a matrix of red, yellow, green, and blue, and now we're changing this into a matrix of 4 by 3 dimension. So 1 0 0 indicating the first sample is red. The second is 1 0 0 also red. 0 1 0 indicating the sample is yellow. So we are putting the 1 at the correct label. And this is one hot encoding. So for more example of yeah, like this. This is one hot encoding. So if the France is the country, we put 1 in here. So we're just forming a 1 into 2-dimensional matrix. So vector into a matrix. Well, this is one hot encoding. Okay, Tensorflow keras.utils import to categorical train on hot to categorical X-tree sequence. XL 1 hot, 2 categorical XL sequence. Yeah, so we just did a one hot categorical encoding. So just like this, we are just changing the matrix. So if you want to see what it looks like, print xtrain on hot.shape. Yeah, you can see how yeah, how should I explain? So from here, yeah, I'll provide a comparison. So print x train sequence.shape. But here it was originally 2000 by 100. Now that we did one hot encoding, it's 2000 by 100 to 100. Just like here. If you're seeing my Google screen, just like this one. So we did one hot encoding. So import TensorFlow as TF. So we are importing the TensorFlow library. Let me know if any of you have a question. In my previous workshops, we actually wrote the actual model, like simple representation of model. But for this workshop, rather than creating our own model, we're gonna use the model already created in the library. And this means that yeah, so we'll use the model from the library. So if you remember from the video, he talked about recurrent neural network, which is RNN. This is what we're gonna use. So from TensorFlow.keras.models, import sequential. TensorFlow keras.layers, import dense simple RN. So you might be wondering what sequential and dense is. We already know what RNN is. It's the recurrent neural network that we talked about in the video. Dense is layer. For the convolution neural network, it's a fully connected layer. So dense is the layer after the recurrent neural network, and typically this is where all the images are spread into one row rather than two-dimensional, and then feed into a dense layer. So that is dense, and sequential allows us to add one layer into another, and you'll see right now. Model sequential, and sequential will allow us to add the layers. Add simple RNN 32 input shape. 100. What this means is we're gonna have 32 what should I call it? It's not node. Yeah, the cells within the hidden layer. Cells. It's the number of cells. Model.add dense In the sigmoid activation, what it does is it allows us to have the value between 0 and 1, and that's the activation function. So just like here in the Google image, it has 1, 0, 0. What it's going to do, the output is going to be like 0.8, 0.1, 0.1. And the 0.8 is going to be the answer since it has the most greatest value. Model.summary. This is what it looks like. This is our own model. RNN model, and we have a dense layer. So we have total parameters, and then yeah. And now we're gonna do an actual training. Model.compile optimizer HTTP loss binary. So what loss function is? It allows us to calculate the loss between the actual value and our calculated prediction. And what metrics does is it allows us to save the accuracy so that we can make the graph later. History, fit, x train, one hot, y train, approx 20, batch size 32, validation data. Excel 1 hot y val. History model.fit x train 1 hot y train epoch 20 batch size validation data Excel 1 hot y val. Value error. Let's see. Unknown loss function. Unknown loss function. Oh, binary. Binary. Should binary. Yeah, it's working. So we're going to do a 20 epochs. Epoch simply means a loop. So now we're officially training. And you can see how the loss and the accuracy. So we have a 50% accuracy so far in our first. So we have accuracy of 50% and loss of 70%. And you can see training accuracy, training loss, validation accuracy, and validation loss. Does anyone have a question or? Might be wondering what SGD is. I mean, I have mentioned the binary cross entropy and accuracy. SGD is a stochastic gradient descent. And if you remember from calculus, the gradient descent allows us to go into the global minimum of the loss function. So stochastic gradient descent for this network, it allows us to approach into global min gradually. So you can see how the loss is gradually decreasing, and accuracy gradually increasing. Takes a while because yeah, we are training with like 20,000 data. That's why it's taking a long time. Does anyone have a question or? Assume everyone is training their data. See, we started from 70, and now we are 59, so gradually decreasing, and accuracy 50 into 70. Training is done, so we have a 70% accuracy. And in order to see about our accuracy, the loss first, let's see PLT. So PLT stands for matplot library history loss plot history now loss. So PLT is not defined. Okay, let's see. Import matplotlib. You can see how the loss has gradually decreased from 0.7 into like 0.58. And now let's see the accuracy. LT.plot history accuracy. LT.plot history val accuracy. LT.show you can see how our accuracy gradually increased, and this means that our prediction, whether the movie content is positive or negative, it is predicting correctly. So we can see how our accuracy is improving. So our final code will be loss accuracy model evaluate Excel one plot eval propose 0 accuracy. Yeah, so our accuracy in total is around 70% correctness. Yeah, so through this coding, we were able to train our model, and the dataset that we have used, the IMDB dataset. And yeah, it looks pretty good. We used the recurrent neural network, and we have trained, the loss gradually decreased. And the reason why the accuracy is not very high is probably because the number of training data set is not a lot, because we're only using 20,000. So I think that is the reason. But I think it went well, yeah. Does anyone have a question or? Wasn't on this interesting topic? Predicting whether the movie comment is a good or not.